Hello, everybody. We're going to start the COMET webinar. So it's the fourth edition. And today we are hosting at the University of Bristol this seminar. So the seminar will be streamed in live. And I know that there is like many different countries. We are over like 40 different countries that look at this webinar, and people in Ecuador especially today. So welcome to everybody. We're going to have today as a speaker Juliet Biggs. She's going to tell us about what drives volcanic unrest, insight from COMET response to recent seismic crises around the world. So the presentation will last about 40 minutes, and after we will have a question. And people that are streaming, you will have like a chat that you can ask your question, and we will take some of them. Thank you.
Okay. Thank you very much. I'd like to say welcome both to the audience here in the Wills building in Bristol, and also to the live audience who are streaming online. It's a privilege to be here today presenting the latest in the series of COMET webinars. So I'm going to talk about some of the recent COMET responses to volcanic unrest around the world. And as I'm talking, if you have any questions, if you're online and you have any questions, please feel free to type them in and submit them as we go, because I've heard there can be a bit of a time delay and it'll speed things up at the end. So please do submit your questions as we go through the presentation. It's widely known that seismic swarms precede major volcanic eruptions, and the slide here shows some recent examples from a compilation by White and McCausland. And this is from really big eruptions at Pinatubo, Montserrat, and Unzen. But actually this compilation includes over 100 different examples of seismic swarms at many different volcanoes around the world. And I wanted to draw your attention to a few key points here. Firstly, the seismicity associated with these events can take place from hours before the eruption through to many years prior to the eruption. And it's often quite distal to the event, either in terms of depth, it can be quite deep, or sometimes it's actually quite laterally distant from the eruptive vent. Oftentimes the seismicity, although it's there, is not particularly well monitored, and this is particularly true for closed systems, which may have not had a particularly well-developed monitoring network if they've been dormant for decades or centuries prior to this eruption. But when we see these seismic swarms at volcanic systems, it poses a question for the decision makers. What should we do in response to these? So on one hand, we know that volcanic eruptions of VEI 4 or greater are almost always preceded by a seismic swarm, and they typically have at least one magnitude 3.9 event. So does this mean if there's a seismic swarm at your local volcano, you should evacuate the entire population? Maybe not, because on the other hand, there have been a lot of seismic swarms which have not culminated in an eruption at all. The seismicity just dies away. So there are various tools available to try and help decision makers do this. So the one on the left is a very financial model of doing this. So this compares the probability of an event occurring to the relative relative proportion of the ratio of the cost of taking an action, such as an evacuation, versus the potential losses if no action is taken. And the problem with this is that you have to be able to quantify both the cost of an action like an evacuation and the potential losses that occur in some kind of units such as pounds, dollars, euros. As scientists, as physical scientists, we tend to actually focus on the other side of this equation, which is what is the probability of a given event occurring. And if you look at the event tree shown on the right-hand side of this figure, you can see that, if we look here, the very first, this is designed to help us work out what the probability of a given event would be. The very first node, which is here, is actually an observation that your volcano is restless, probably an observation of seismicity. But the very next node is to determine whether this seismicity is caused by a magmatic intrusion or some other kind of process, tectonic or hydrothermal, for example. And this is often quite difficult to do from seismicity alone. So what I'm going to do in the course of this webinar is actually look back at 3 recent seismic swarms and try and think about what we've learned from using satellite observations to augment the ground-based seismic data that was available when these events occurred. So I'm going to go through three examples: Santorini in Greece, 2011 to 2012, Chile, Serra, Negra. This is a pair of volcanoes on the border between Ecuador and Colombia between 2013 and 2014, and then finally Agung in Bali in Indonesia, where the seismicity started just at the end of last year. In each one of these events, COMET has been using satellite data to investigate the causes of these seismic swarms. We've had very different results in each case. So obviously this work hasn't been done by me in isolation. It's been done very much as a group effort by the research group and by the wider COMET network. Each one of these has been led by a different person. This is Fabian Albino, who's been working on the events at Agung. Here in the middle, this is Susanna Edmeyer, who was a postdoc at Bristol formerly and is now in Leeds, who worked on Chile, Serra, Negra. And this is Michelle Parks, who is a PhD student in Oxford and is now working at the University of Iceland. So I'd like to say thank you to the three of those for leading these projects we're going to talk about today. So before we get on to the details, we need to think a little bit about the framework that we have for understanding volcanic unrest. And volcanology right now is going through a bit of a paradigm shift. So the traditional view of a magma plumbing system is that we have this elastic-sided magma chamber, a single magma chamber beneath a given volcano. And as magma moves into this balloon, it expands, it swells up, it causes uplift at the surface, and the stresses around the edge of the balloon trigger lots of little earthquakes to occur, which is what drives the seismic swarm. In recent years, though, mainly driven by petrology, we've completely revised this view of magmatic plumbing systems. We now imagine a vertically extensive mush column, which is largely crystalline for a lot of its time and a lot of its space. And within that are isolated pockets of high melt fraction. And now the petrologists have really good constraints on the depth and the pressure at which these different processes are taking place. But I think we have to look towards tools such as geodesy and seismology to try and tell us something more about the lateral extent of these systems. And that's something I've been particularly interested in recent years. Another question is, what is the timescales of magma recharge? The traditional view in this case has been that magma chambers are recharged incrementally, continuously over long time periods, and an eruption occurs when a given threshold is reached. And this is directly analogous to theories of the earthquake cycle, in which strain is accumulated over long time periods due to the motion of tectonic plates, and then an earthquake occurs when a given threshold is reached. And actually there are some examples that support this from the volcanic literature. This picture on the bottom right here shows the link between a repose interval and an eruption volume. And if we have a model of continuous recharge, we would actually expect there to be a linear relationship. The longer it is since the last eruption, the larger the volume of erupted material that's going to come out. And this example is from Santorini, and we see that relationship quite clearly. Once again, petrologists are throwing a spanner in the works here, particularly by looking at diffusion chronometry. And they suggest that actually the repose interval of crystals prior to eruption is actually much shorter than the repose interval between eruptions, suggesting that actually magma recharge may be episodic rather than continuous. So this is a question that we want to try and answer. And finally, what can we learn from the seismic swarms about the processes that are driving them? And this is from that compilation of White and McCausland, and they looked at the relationship between the cumulative seismic moment from the seismic swarm and the intruded volume, and they found a clear linear relationship. And actually, the straight line in this figure here, this straight line here, this actually comes from induced seismicity from people looking at wastewater injection into shallow wells, and you can see that the observations from volcanology matches this particularly well. So one of the questions is, can we use this kind of relationship to predict eruption size? And before we can do that, we have to really understand what is driving these seismic swarms. And actually, this is where we want to look to deformation to see if we can answer some of these questions. So let's get started on some of these examples. To start with, let's look at Santorini in Greece. So Santorini is a very famous volcanic system, familiar to many of you. It's very popular with both honeymooners and undergraduate geologists. A good combination. So the geologists are obviously interested in looking at the remnants of these caldera-forming eruptions. They happen every 20 to 30,000 years. The most recent occurred in 1620 BC and is credited with destroying the Minoan civilization. But on a shorter timescale, on a timescale more compatible with monitoring data, There are also much smaller dome-forming eruptions, and these happen on timescales of decades to centuries. The most recent of which was actually in 1950 AD, and we actually have, it's a recent event, we have good photographic evidence, such as the one shown on the right here. So the seismic swarm at Santorini that I'm going to talk about today happened 2011 to 2012. And you can see on the picture on the left here is the seismic locations. The picture on the right here is a map of the surface deformation that we made using satellite data. So in order to make this, we use a technique called INSAR. INSAR compares the phase of two successive radar images, and it uses this to look at how the distance between the satellite and the Earth's surface is changing and tell something about the displacement of the ground in the direction of the line of sight of the satellite. So in this particular image, we can see there's about 15 centimeters of uplift of the COMET Islands in the center of the caldera here, and small amounts of uplift around the edge here. If we actually look at the satellite images themselves, what I've got here is actually two separate images taken by different satellites in different orbital directions. So this is Envisat data taken from a descending track, and the one at the bottom here is TerraSAR-X data taken from an ascending track. And in both of these cases, we see significant amounts of uplift, but there is a difference in the spatial pattern. You can see that in this upper figure here, the uplift is mainly to the north of the COMET Islands, and this one is mainly to the west of the COMET Islands. And the different patterns from the different line of sights tells us that there's got to be a significant amount of horizontal motion occurring. So we want to fit a model to this data to try and tell us what the source of this deformation is. The simplest possible source we can imagine is a point source of inflation, and if we and the central column here shows the model predictions. If we put a point source at the location of this red dot here at a depth of about 4 kilometers, and we can see that we match the patterns in both the ascending and the descending line of sight images quite nicely. And the column on the right here is the residual image, which shows that we've actually managed to recreate the systematic signal in the data, and what's left is just a random residual. What's particularly exciting about this case in Santorini is that we can actually take some of this modern technology and some of the measurements we've made with satellite techniques and go back and compare to observations made with much older technology. And in this case, triangulation measurements, which were actually made in the 1950s, not that long after that last eruption that I just showed you. And what we find is that the measurements from the 1950s to the present day are actually very similar to what we see if we just think about that current seismic swarm. And it tells us that there actually hasn't been any significant deformation since that last eruption. This picture on the right here just shows you the residuals are within the areas of the observations. So this tells us immediately that this model of continuous recharge really can't be applied here. All the magma that's been fed into this system under Santorini's come in the last 2 years. There's been nothing else since that last eruption. And so we actually now have to have a revised model of this timescale of magma recharge. And this fits in much better with what petrological observations are telling us, in that the residence time of magma prior to eruption is actually very short. We can also look at where this plots on this image of seismic moment, and what we find is that the intruded volume, 10 to the 7 cubic meters, and the seismic moment, 10 to the 15 Newton meters. So the volume is actually much larger than would have been predicted just by looking at the seismic moment of these events. So one possibility actually is that there's different mechanisms driving the seismicity and the deformation, or that some of this deformation is taking place aseismically. It's also worth noting that the majority of the examples shown on this trend line are actually from seismic swarms that went on to eruption, and the example at Santorini here clearly did not go on to an eruption. So perhaps there's a systematic difference between eruptive and non-eruptive events. But we can actually look in more detail at the temporal characteristics of the displacement and see what we can learn from this. So what I showed before was was actually a sum of many satellite images added together. We can actually separate these back out, and we can create a time series of deformation, which is what's shown in this on the right here in these red dots. Each one of these dots corresponds to a new satellite image being collected, and we can combine that with GPS observations. Now, GPS observations are only measured at a handful of points around the island, but they have fantastic temporal resolution. So we can combine the good spatial resolution of the satellite data with the good temporal resolution of the GPS and do a joint inversion to find out how the volume changes with time. And we get this green line here. And we can see that this is not a continuous gradual increase. There's actually two distinct pulses of deformation here. We can also see, if we compare this line here, I've kind of highlighted these to make them a bit more obvious. You can see these two pulses of change in the volume. You can also see that there's a similar pattern in the seismicity. So there's an increase in the seismicity in this first period. This is shown as the cumulative seismic moment. Then it falls off. Then there's another increase in the seismic moment, and then it falls off again. So this suggests to us that actually what we have here is two pulses of magma injection, but with some continued deformation in between. And one of the beauties of working as part of the COMET team is that you can call on expertise, a wide range of expertise and resources from within COMET. And so we worked with James Moore, who produced a model, who refined our model of a point source, surrounded it by a viscoelastic shell with viscosity mu and radius R2, and adapted the analytical solutions to take two pressure pulses, which is shown by this red line here. So we have a pressure increase during the high seismicity periods, and then no change in pressure during the low seismicity periods. And the results of this model are shown by this red line here, which you can see match the data, the deformation data, very nicely. So what's happening is that seismicity is occurring during the pulses of when magma is being fed into the system, but during these quiet pulses, there's no seismicity, but deformation is still occurring because there's a response in this viscoelastic shell, which represents the hot thermal aureole surrounding the magma chamber. And we can fit this model using fairly standard parameters, which gives us reassurance that the model is also realistic. So if we look at this, we can actually see that some of this deformation isn't really caused directly by the magma injection. It's actually caused by the viscoelastic response. And this might adjust our measurements here, might explain why we have this observation that maybe some of the deformation is aseismic. And it probably does, but by something on the order of a factor 2. And this mismatch we can see here is actually more like 2 orders of magnitude. So we still have this remaining mismatch between these observations and the predicted trend line. But obviously this is just one example. We need to see if this is systematic. Does this apply to all non-eruptive seismic swarms, or is there something anomalous happening with Santorini? So we're going to look at another case study. This is Chile's Serra Negra. So Chile's and Serra Negra are two different volcanoes. They lie on the border between Ecuador and Colombia. They're pretty remote. And when the seismic swarm started, remarkably little was known about these volcanoes. The last eruption of Volcan Chiles is estimated to be about 160,000 years, and the most recent eruption at Serra Negra is not particularly well dated, but we know there was a debris avalanche that has to be at least 3,000 years old. So those are the last evidence of really significant eruptions. Actually, people have looked at more recent records and found evidence for seismicity and changes in the fumarole behavior that have been going on in the 19th and 20th centuries. So maybe this is a volcano that is persistently restless. But just because there haven't been any historical eruptions doesn't mean there couldn't be a historical eruption. And on average, if we look around the world, there's an eruption at a volcano with no historical record that occurs roughly once every 2 years. So just because there is no historical eruption doesn't mean we should be any less concerned about these volcanoes. In fact, at Chile Serra Negra, it wasn't a single seismic swarm. There was actually a sequence of distinct seismic swarms. The first one was in October 2013. The second one was in February to May 2014. And the third one, which is the one I'm primarily going to talk about, was September to December 2014. In fact, there were two earlier seismic swarms, actually particularly key because it allowed the volcano observatories in Ecuador and Colombia to actually deploy some equipment, but they also contacted us at that time, and we started making satellite observations back in early 2014. We didn't actually see anything particularly interesting at that time, but we were already looking at this volcano long before this major seismic swarm started to happen. So the seismicity was located about 30 kilometers to the south of Chile's Serra Negra. So this picture here, you can see these are the two volcanoes up here, right on the border between Ecuador and Colombia. And the seismicity was actually on the Ecuadorian side of the border here. By October 2014, there was over 5,000 events per day. And the magnitude of these events was increasing, and they culminated in a magnitude 5.6 earthquake on October the 20th. So this caused the volcano observatories in both Ecuador and Colombia to set the alert level to orange, which corresponds to eruption expected within days to weeks. And given the previous statistics that many magnitude VEI 4+ eruptions are preceded by seismic storms, typically with magnitudes in excess of 4, this was obviously a sensible decision. But what happened next? Well, we were looking at seismic images of the event, and this is an example. So Ecuador and Colombia are not necessarily the easiest place to use INSAR. They have a lot of vegetation, a lot of steep topography, and also quite a lot of water vapor. So this is the kind of quality of the images we were getting. So here you can see Serra Negra, and Chile is just to the east of it here. And this is the fringe pattern. We can see this is a Cosmos SkyMed interferogram. And you can see there's clearly some deformation going on, but it's not immediately obvious what's causing it. And the initial interpretation was this was uplift caused by the same source that was causing that seismic storm. But actually, as we started to collect more data, and you can see a couple more examples on the right here, and to start to process this data with better techniques, improve the quality of our images, we started to realize that actually the shape of this deformation pattern was much more typical of what you would expect to see in a reverse earthquake, a normal that you might expect to find in a thrust environment like the Andes. So we actually tried to model this using instead of using the kind of magmatic source, using a typical earthquake source, using the Akada solution. And these are our solutions. So the column on the left here is the data again from ascending and descending orbits, and this central column is our predictions based on a model of a thrust fault with significant amounts of right lateral motion, which also fits in with the tectonic settings. We know there's some sliver transport in this region, and you can see from the very low residuals in this right-hand column that actually this model matches the data particularly well. So where is this source? So this is the final model. You can see that there's a significant amount of both strike slip and thrust motion across the fault plane here. And the fault source actually aligns with a well-known fault zone. This is an extension of the Romerol fault that runs through Colombia. And it has been the source of earthquakes in the past. There were two historical earthquakes in August 1868, one near the town of El Angel that was 6.5, one near the town of Ibarra that was 7.5. So this event is actually not a surprising event to occur on these tectonic faults. But we need to understand what its relationship to the magmatic activity that was happening at the same time is. So actually, if we look back at the GPS sites, as I said, it's quite significant that there'd been some previous seismic storms because it meant there were 2 GPS sites operating in the region. And you can see the offsets here associated with this magnitude 5.6 earthquake, but you can also see there's a significant amount of inflation preceding this event. And with 2 GPS points, it's hard to get a very accurate location on this, but it lies somewhere to the south of our 5.6 earthquake, and it's quite deep. It has to be somewhere between 13 kilometers and 25 kilometers in depth. So how do all these events fit together? And this is a cartoon that Susie put together to try and explain the relationship between all these different processes. So this thing here, this is the magnitude 5.6 earthquake. We have the volcano de Chile and Serra Negra here, and here's that deep pressure source that was detected by the GPS. So what we think was happening was that during the time period of the seismic storm, between the 1st and the 19th of October 2014, this deep source was pressurizing. It was unclamping all the faults in the region, including this part of the El Angel fault system. And this was causing the observed seismic storm, causing the uplift, and eventually unclamped this existing fault system so that the preloading of the tectonic stresses was actually released. Once that earthquake occurred, that actually changed the stress in the local environment as well. and that actually reclamped a lot of the region, particularly the region around this pressure source. And so at that point, the pressurization stopped, and the seismicity gradually began to decline. So once again, we can take these observations and think, how do they fit in with this this overall picture of seismic moments and injected volume? Well, if we look at the cumulative seismic moments and compare it of the swarm and compare that to the volume of injection detected by the GPS, we actually end up in a very similar location on this plot to what we saw at Santorini. Both of those events ended with no eruption, I should remind you. However, if we choose to include the magnitude 5.6 earthquake, we end up right back on that line. So whether or not it's valid to include the 5.6 earthquake is a good question. So we think a lot of the moment released in this event was not related to the magmatic processes at all. It was actually a tectonically loaded fault that was really nearly unclamped by this by the transient stresses associated with the magmatic system. So other conclusions from this event are that stress triggering can occur over significant distances laterally as well as vertically, and actually the mechanisms driving these seismic swarms are pretty varied. So the seismicity is probably driven by hydrothermal fluids, and the largest earthquake is actually probably caused primarily by tectonic loading and then triggered by the magmatic processes. We're going to go on now to the third of these events. This is the most recent at Agong volcano in Indonesia. So Agong is famous. It had a VEI5 eruption in 1963, which actually caused over 1,000 fatalities. It's located here on the island of Bali, and it's actually got a neighboring volcano. It's called Batu, and several months after this initial eruption in 1963 of Agong, Batu started erupting and actually continued erupting for several years afterwards. So what about more recent times? Well, this is a schematic showing the 2017 seismic swarm, which started which kind of spanned September to October. There was a lot of seismicity, 1,000 events per day, including a lot of felt seismicity by the local people. There were also significant changes near the summit of the volcano, changes in fumarole behavior, and also some explosions. And this triggered the evacuation of 150,000 people, and the alert level was actually set to red, which means eruption is ongoing. However, you can see that the seismicity actually died off, and the first really significant eruption actually didn't take place until November the 21st, and there was an extrusion of a lava dome over the next 10 days or so, with a volume of about 10 to the 7 cubic meters. Now, the seismicity in this swarm was actually located midway between Agong here and Batu over here, and the original hypothesis was actually that you have a magma reservoir that's stressing a nearby fault. The magma reservoir is actually located directly beneath the summit of Agong, and the seismic events are actually distal to that magma source. So we're going to reassess that by looking at some of the satellite data. So once again, Bali is not the easiest place to carry out satellite measurements. This is the kind of interferogram that was being produced both by our group, but also by many other people all around the world. You can immediately see some fringes around the summit of Agong here, which caused a lot of people to send this information to the Volcano Observatory to announce it on social media. But actually, if you have some experience working in tropical volcanoes, you realize that actually it's very important to understand the atmosphere when you're interpreting these observations. So water vapor in the atmosphere affects the passage of radar waves. And if you have a very tropical atmosphere and a very steep volcano, you typically end up with fringes around your volcano that are simply caused by the water vapor content of the atmosphere and have no relationship to what's happening on the ground. So we worked together with the GACOS group in Newcastle, these high-resolution weather models, to produce corrections for interferograms. And this is what their prediction of based on the weather conditions on that day. And you can see there's a pretty good match here between the predictions just based on the weather model and the kind of fringes that we see at Agong. And you can see the residual here actually removes almost all of those fringes. So this apparent deformation is actually caused not by the volcano, not by the magmatic processes, but actually just an artifact of the atmospheric delays in our data. So this has raised some issues to do with open access data, how you communicate the information from open access data, first with the observatories and also with social media. We posted this, both communicated it directly to the Volcano Observatory and also posted it widely on social media to try and correct some of the misinformation that was going around at the time. So when we look at the corrected interferograms, actually we see that there's not an awful lot of deformation in the individual image. And that's what we thought for several months, actually, whilst the seismic storm was ongoing. And it wasn't actually until a few months later, when we collected a larger archive of data, we carried out all these atmospheric corrections, and we started compiling the information. But we realized actually there has been a deformation signal going on during the seismic storm. So here, once again, we have data from ascending and descending tracks. The top row here is prior to that seismic storm, and we can see there's no significant deformation taking place, and it's kind of like a baseline measurement. But during the seismic storm, we can see significant amounts of uplift on the north flank, as on here, on the order of about 8 to 10 centimeters. Once again, we can see that this pattern of uplift is not in exactly the same place. It's slightly further towards Batura in this ascending image, and slightly further towards Agon in the descending image, which suggests there's a significant amount of horizontal deformation. However, it doesn't really conform to any of the standard models that we might want to use, a point source or a dike. And the reason for that is probably actually that there's extreme topography at these volcanoes, so the deformation patterns we're used to seeing is actually distorted by that topography. So the only way to really try and understand this is to use finite element model. So Fabian turned to console, and he made a finite element model which took into account the three-dimensional topography, and he tried to fit the deformation pattern with a magmatic intrusion, with the parameters that you can see here, the dike-shaped magmatic intrusion. And the best fit model is that of a dike which lies along the axis between Agon and Bali. And you can see this does a good job of fitting the data both from the ascending track and from the descending track. In the residuals, you can see that it's actually fit this deformation pattern on the north flank. But what is left behind is this little signal of uplift right near the summit of Agon. We've actually had a look at that. And that's probably less than a kilometer deep, probably in the top few hundred meters. And that's probably associated to some of these changes in the fumarole field that were being observed at the time, something hydrothermal. But we want to focus for now on this deeper magmatic signal. So the location of this dike midway between Agon and Batura raises some interesting questions. So firstly, it seems that the seismicity is actually not distal seismicity. It's not triggered seismicity on a nearby fault system, as we saw in Chile, Serra, Negra. It's actually proximal to the magma intrusion itself. So this seismicity is immediately surrounding the location of that dike intrusion. But we also had some questions about why is this dike intrusion located here? It suggests that there might be a common source between Agon and Batura, and it also suggests there might be a common trigger for the eruptions at Agon and Batura, and that's sort of what we saw in 1963. So perhaps that shouldn't have been a surprise. But what's controlling the location and the orientation? So the first thing to turn to is the tectonic stress field, and we found in Chile, Serra, Negra actually that the orientation of the earthquake fit the tectonic stress field very nicely. In this case, it doesn't fit it at all. So there aren't that many examples, but there are a few regional earthquakes that have happened. And this plot shows the principal stress directions of this dike by these black symbols here, and compares them to the principal stress directions associated with these regional earthquakes. And you see there's a very poor correspondence between them. The other possibility is that actually there's loading, topographic loading by these extremely large volcanic edifices that I keep mentioning. And that topographic loading is actually changing the stress field locally beneath these volcanoes. And so once again, we used the finite element modeling solution to try and work out what the orientation of the stresses caused by this topographic load would be. And what we find is that actually immediately at this location between these two volcanoes, the stresses correspond extremely nicely to, they're shown by the red dots, by the way, correspond extremely nicely to the orientation of that dike intrusion. So in this case, it seems that the tectonic stresses aren't so important, and what's actually dominating here is the local stress field caused by the topography. So if we try and put this together, we now think we have some kind of deep source between Agon and Batur, which is feeding a dike intrusion. But how does this relate to what's going on at the surface? So initially, during the seismic storm, we see some kind of shallow signal, maybe to do with the hydrothermal system. But actually, there's a several-month time lag before the eruption starts to take place. The main eruption starts to take place. And actually, if we look back in the record from both the eruption in 1963 and actually the geological record of eruptions that took place before that, we find that magma mingling is really important. So we find that those eruptions were almost certainly triggered by a mafic injection into an andesitic magma reservoir. So we're hypothesizing that the same situation took place here, that there's what we're actually observing is the mafic intrusion part of this system, which lay between Agon and Batur. And what's happened is that has intersected a pre-existing andesitic shallow chamber, caused magma mingling, and the time scale of mixing is typically thought to be on the order of weeks to months. So this time scale, the delay before the eruption started, is very consistent with that. So how does this example fit back to our observation? Well, if we just compare the moments of the storm with the dike intrusion volume, we actually get a very good correspondence there. But actually, we have some other observations. So that lava dome, kind of pancake-shaped lava dome that grew at the top of Agon in November, we actually have some estimates of the volume of that. They're about 10 to the 7 cubic meters. So if we actually take that as the volume, we'll realize it actually lies off the trend here. So although it did a reasonably good job of linking the intruded volume, it actually did a fairly poor job of predicting the erupted volume here. So this example is particularly important because it's showing us about something about the connection between neighboring volcanoes. And that's something that really hasn't been taken into account much when we're considering eruption risks. There may actually be eruptions from nearby volcanoes simultaneously triggered by common magmatic plumbing systems. It illustrates the topographic control on the plumbing systems, and it also shows that these distal seismic storms, sometimes in the case of Chile, Serra, Negra, can be caused by stress transfer, but they can also be a sign that there's an intrusion taking place that's actually some distance away from the eruptive vent. And so I'm going to just wrap this talk up with a few concluding comments. So I think what I've tried to show here is that actually satellite observations of deformation can be really critical in understanding the causes of volcanic unrest. So the seismic swarms I've shown, they had many similarities in terms of the seismic data, but actually they were driven, the satellite deformation observations have enabled us to demonstrate they're actually driven by quite a wide variety of mechanisms. So some of it's due to magma intrusion, controlled by topographic loading. There's also tectonic loading played an important role. Viscoelastic relaxation and the presence or absence of hydrothermal fluids have all influenced both the seismicity and the deformation patterns observed at these volcanoes. So whilst it's really valuable, very interesting to consider these kind of global rules that you can apply to all systems, when you're actually trying to deal with a crisis situation at an individual volcano, there really is no substitute for detailed observations. So that's why the work of, I'd like to kind of acknowledge the work of several organizations who are really putting a lot of effort into making sure this kind of data is available. So firstly, the space agencies who contribute much of this data free of charge through various different kinds of agreements leading to disaster risk reduction. To the volcano observatories, who are several of them listed here, really get a lot of benefit from two-way communication in comparing our satellite observations with their ground-based observations, and trying to produce something that's actually useful for decision making. And also to several groups who are really invested heavily in processing this data routinely and making it available routinely, COMET, CEOS, and the USGS Powell Center. So I'm going to leave you with a final slide. Quite a lot of this work has already been published. Some of it is still in review. For those of you on the web, you can look up this slide later if you want to go and refer to these for any further details. So that's the end of the presentation. I think we're going to open to questions now. I don't see any yet online, but maybe Fabian or Lou want to come and double check that this is working properly. Does anyone in the room have any questions whilst? Yes.
I realise this may be quite soon, but having been having video every other day eruptions over the last weeks, is there any data from that, or is there a pre-seismic form from those, or is it
Okay, so the question was, Agon continues to have activity now, and is there any information related to that? So obviously the situation is being monitored by the Volcano Observatory on the ground, and they are really the people to offer authoritative advice on these things. But we are still looking at the satellite data, and we haven't seen any obvious changes yet. We have a better idea of what to look for. Now we've kind of got used to doing the right corrections and things like that, so it'll probably be quicker than it was last time. I think it is important to note that actually this information about the dike didn't come out for several months afterwards, so the people really to refer to are always the volcano. Do you have any other questions? Yes, question from Steve Sparks.
Juliet, could you just explain a little bit how you've got volumes and you plotted it on a cumulative seismic moment, and I'm not quite sure how you relate. You're plotting the volume, but what are you plotting it against?
So that plot, I can go back, it's a bit tricky, unfortunately. Okay, so the question from Steve Sparks, who asked me to explain the plot of volume against cumulative seismic moment. So the cumulative seismic moment is just taking the moment of every earthquake in the seismic swarm, adding them up. And actually, in practice, the small ones don't really matter so much. So as long as you get everything within half a magnitude of the largest event, you probably captured most of the information there. So even if the seismic record isn't complete, you can do a pretty good job of estimating it. Now, so that compilation from Whiteman McCausland, actually the data that they use comes from a range of different sources. So for some of the basaltic events, actually that's the erupted volume, the lava volumes. And for some of it, it's other ways that they've studied the intruded volume. And I actually couldn't tell you what every single data point on that is, but there is a compilation that details that. The ones I've put in there, actually, I think it's a good question, actually, because there's lots of possibilities about which data you choose to include and which data you choose to throw out. So in the examples I've shown, if I made certain choices, I could make it fit that trend line, but I could equally make other choices that would lie off that trend line. So how you decide which parts of the deformation and which parts of the seismicity are related to your event and which ones are related to some other process is a decision.
Some measure of displacement.
Oh, yes.
How do you convert that into a volume, or vice versa, convert the volume of the magma into a displacement? That's what something is.
So those are just empirical measurements. The ones plotted there. So each data point they're two independent parameters plotted against each other. Yeah. But actually, you could think about how you might choose to do this. So some people have created something called a geodetic moment. So a seismic moment is just the amount of slip multiplied by the area of a plane. So you could, if you think of any kind of source as a rectangular opening, you could actually look at the amount of opening multiplied by the area. And actually that would, I did do those calculations, and that would produce a trend line that lies several orders of magnitude away from that. And that's probably because not all of that opening is actually being translated into shear on nearby fault planes. So that's probably telling you something about the seismic efficiency of translating the opening into shear on those pre-existing fault planes.
Yeah, we have a question from people online. So Cyril that asks, hello, the dike that has been modeled in COMSOL for Agum volcano was the result of forward or inversion model?
So perhaps Fabian is best placed to answer that. He did the COMSOL modeling. That is an inverse model. Do you want to tell us how you did it?
Yeah, so we start by looking forward modeling for the different source points, like spherical, oblate, and dike source. And after we did an inversion to optimize the parameter. So yeah, for the question, it's an inversion model. Okay, so.
Okay. So if there are any other questions in the room, and Cyril says, "Nice job, thanks." Thanks, Cyril. If there are no other questions from the audience, I think we can.
Okay. So yeah, we're gonna close this session. I would like to thank Jonathan Weiss, that's the coordinator of the COMET webinar, and we will keep you posted for the next one. And thank you all here in Bristol and in the stream. Thank you.